Welcome to this lesson on TRIZ, the theory of inventive problem solving. TRIZ is a powerful systematic approach to innovation that was developed by analyzing thousands of patents to find patterns in how inventors solve problems. TRIZ was developed by Genrich Altshuller, a Soviet engineer and scientist who studied over 200,000 patents and discovered that problems and solutions repeat across industries. He found that only about 1% of patents contain truly novel solutions. The key insight is this: innovation is not random. It follows predictable patterns. And if we understand these patterns, we can systematically generate innovative solutions to technical problems. TRIZ comes from the Russian phrase meaning theory of inventive problem solving. It provides a systematic methodology that can be learned and applied by engineers and problem solvers. One of the core tools in TRIZ is the 40 Inventive Principles. These are 40 strategies that have been used repeatedly across different fields to solve contradictions and generate innovative solutions. Let's explore some key principles. Principle 1 is segmentation. Divide an object into independent parts or make it sectional for easy assembly and disassembly. Example: instead of building one large cargo ship, we create modular shipping containers. This revolutionized global trade by making loading, unloading, and transfer incredibly efficient. Principle 10 is preliminary action. Perform required changes to an object fully or partially in advance. Prearrange objects so they can come into action immediately. Example: prefabricated construction and IKEA furniture. Instead of cutting and assembling everything on site, parts are manufactured in advance. This reduces construction time from months to days. Principle 15 is dynamics. Make characteristics of an object or environment automatically adjust for optimal performance at each stage of operation. Example: variable geometry aircraft wings. Modern fighter jets can adjust their wing configuration for optimal performance at different speeds, from takeoff to supersonic flight. Now let's look at an inspiring real-world example of TRIZ thinking. In 1968, Dick Fosbury revolutionized high jumping with what became known as the Fosbury Flop. The problem was simple: how can an athlete jump higher over a bar? For decades, athletes used techniques like the scissors kick or the straddle method. In traditional methods, athletes would go over the bar face first, with their belly facing down. This meant their center of mass had to go over the bar, requiring tremendous force. Fosbury applied TRIZ Principle 17, move to another dimension. Instead of trying to push the center of mass higher, he asked, what if my center of mass doesn't need to go over the bar? By going over backward with an arched back, Fosbury's center of mass actually passed under the bar while his body went over it. This was physically revolutionary. Let's understand the physics quantitatively. This involves the concept of center of mass and rotational dynamics. The height of the center of mass equals the bar height minus the arching distance. By arching your back, you create a gap. In traditional methods, the center of mass typically had to clear about 10 centimeters above the bar due to body geometry. With the Fosbury Flop, the center of mass can actually be 10 centimeters below the bar height while the body clears it. That's a 20 centimeter advantage. This 20 centimeter difference is enormous in high jumping. It's the difference between an Olympic medal and not making the finals. After Fosbury introduced this technique in 1968, high jump world records increased by over 30 centimeters in the following decades. Today, virtually all elite high jumpers use the Fosbury Flop. Let's look at another inspiring TRIZ application. How do you refrigerate food and medicine in areas without electricity? This is a life-saving problem in developing countries. In rural Africa and Asia, many communities lack reliable electricity, but they desperately need refrigeration to store vaccines, medicines, and food safely. The solution uses TRIZ Principle 2, taking out. Remove the part that's causing the problem. In this case, remove the need for electricity entirely. The solution is the Zeer pot, also called a pot-in-pot refrigerator. You place a smaller clay pot inside a larger one with wet sand between them. As water evaporates from the sand, it absorbs heat energy from the inner pot. This is the same principle that cools your skin when you sweat. The heat removed equals the mass of water evaporated times the latent heat of vaporization. The latent heat of vaporization for water is about 2.26 times 10 to the 6 joules per kilogram. This is a huge amount of energy per unit mass. Let's calculate. If 100 grams of water evaporates per day, that's 0.1 kilograms. The heat removed is 0.1 times 2.26 times 10 to the 6, which equals 2.26 times 10 to the 5 joules per day. Dividing by the number of seconds in a day, that's about 2.6 watts of continuous cooling power. Not huge, but enough to keep food 15 to 20 degrees cooler than ambient temperature. This simple technology increases food storage time from about 2 days to 20 days in hot climates. It has saved countless lives by preserving vaccines and preventing food waste. The beautiful part? It costs about $2 to build from local materials. This is TRIZ at its finest. Elegant, accessible, and life-changing. Let's examine another brilliant TRIZ application, the Phillips screw. You might think a screw is just a screw, but this innovation transformed manufacturing. In the early automotive industry, workers had to carefully align flathead screwdrivers with screw slots. If they applied too much torque, they'd strip the screw or damage parts. The flathead design was problematic. It required precise alignment and provided no torque control. Henry Phillips solved this with TRIZ principles. Phillips applied Principle 25, self-service. Make an object service itself by performing auxiliary helpful functions. The cross-shaped design is self-centering. He also used Principle 11, beforehand cushioning. The tapered design causes the driver to cam out when torque exceeds a threshold, preventing over-tightening. The genius is in the controlled cam out. When you apply too much torque, the screwdriver pops out of the screw head. This seems like a flaw, but it's actually a built-in torque limiter. The maximum torque before cam out depends on the axial force, the radius, the coefficient of friction, and the taper angle alpha. For standard Phillips screws, cam out typically occurs at 2 to 4 Newton meters, which is perfect for most assembly applications. This innovation was crucial for mass production. Assembly line workers could work faster without worrying about over-torquing. The American Screw Company licensed it in 1936, and within years it became the standard. Now you might be asking, if TRIZ is so powerful, why don't more people use it? Why isn't it taught everywhere? This is an excellent question. The answer is that TRIZ requires systematic, disciplined thinking. It's easier to rely on trial and error or incremental improvements. True innovation requires studying the contradiction. In TRIZ, we say every difficult problem contains a contradiction. You want parameter A to increase, but that causes parameter B to worsen. Conventional thinking compromises. TRIZ thinking eliminates the contradiction. Let's look at a classic engineering contradiction. You want a material that's strong, but you also want it to be lightweight. Traditionally, these are opposing requirements. Steel is strong but heavy. Aluminum is light but weaker. Conventional engineering would compromise, maybe using a steel-aluminum alloy with moderate properties. But TRIZ says, eliminate the contradiction. Apply Principle 1, segmentation. Don't make it solid. Make it hollow or create a structure. The result is truss structures, I-beams, and honeycomb materials. These structures achieve both high strength and low weight by distributing material intelligently. Modern aerospace structures can achieve strength-to-weight ratios 10 times better than solid materials. This is why aircraft can fly and why bridges can span kilometers. We measure this with specific strength, stress divided by density. Optimized structures maximize this ratio. TRIZ provides a systematic tool called the contradiction matrix. It's a 39 by 39 table that maps improving parameters versus worsening parameters. There are 39 standard engineering parameters, things like speed, strength, temperature, reliability, manufacturing complexity, and so on. When you have a contradiction where improving parameter A worsens parameter B, you look up that cell in the matrix. It suggests which of the 40 principles are most likely to resolve that specific contradiction. For example, you want to increase speed, but that usually increases energy consumption. The matrix might suggest Principle 35, parameter changes, or Principle 15, dynamics. Remember, this isn't just guessing. It's based on analyzing hundreds of thousands of successful patents to see which principles were actually used to solve similar contradictions. Let's apply this to a real problem. How do we reduce aircraft drag without compromising lift? This is a fundamental contradiction in aerodynamics. Smooth surfaces minimize drag, but airplane wings need roughness to maintain attached flow and generate lift, especially at low speeds. The TRIZ matrix suggests Principle 15, dynamics. Make characteristics change to be optimal at each stage. The solution is leading edge slats and trailing edge flaps. During takeoff and landing when you need maximum lift, they deploy to increase wing area and curvature. During cruise at high altitude, where drag is critical, they retract to create a smooth, streamlined surface. The wing adapts dynamically to flight conditions. The lift coefficient CL equals 2 times lift divided by density times velocity squared times wing area. The drag coefficient CD equals 0 lift drag plus the induced drag term, which depends on the lift coefficient squared. Flaps can increase maximum lift coefficient from about 1.5 to 3.0, which is a factor of 2 improvement. This allows aircraft to land at much lower speeds, reducing runway length requirements. One of the most profound insights from TRIZ is that technical systems evolve according to predictable patterns. Altshuller identified 8 laws of technical system evolution. Law 1 is increasing ideality. Technical systems evolve toward increased ideality, which means more useful functions with fewer harmful effects and less cost. We can express ideality as the sum of benefits divided by the sum of costs plus harms. The ideal final result is when this ratio approaches infinity. Consider lighting. We went from candles to oil lamps to incandescent bulbs to fluorescent to LED. Each step increased the light output per unit cost and energy. Candles produce about 1 lumen per watt. Incandescent bulbs give 15. Fluorescent gives 75. Modern LEDs produce 150 lumens per watt or more. That's a 150-fold improvement in efficiency. Law 4 is transition to the micro level. Systems evolve from macro level to micro level solutions, from mechanical to thermal to chemical to electronic. Early computers used mechanical gears and relays, then vacuum tubes, then transistors, then integrated circuits with billions of transistors. The functions moved from macro to micro scale. This raises a fascinating question. Can we use TRIZ to predict what innovations are coming next? Can we see the future of technology? The answer is yes, within limits. TRIZ patterns suggest probable directions for evolution, though the specific implementation may surprise us. For example, TRIZ would predict that energy storage will transition to the micro level. Instead of large batteries, we might see energy stored at molecular or atomic scales. And indeed, this is happening. Researchers are developing nanostructured battery electrodes and even exploring quantum batteries that leverage quantum effects. The key takeaway from TRIZ is this. Innovation doesn't have to be random or rely on genius. It can be systematic, learnable, and repeatable. The 40 inventive principles give you a structured approach to generating solutions. When you face a tough problem, you can methodically try different principles. The contradiction matrix helps you focus on the most promising principles for your specific situation, saving time and effort. TRIZ has been used by companies worldwide to generate thousands of patents and solve problems that seemed impossible using conventional methods. Let me summarize what we've learned about TRIZ and why it matters. TRIZ reveals that innovation is not random magic. It follows identifiable patterns that can be learned and applied. We saw inspiring examples, the Fosbury Flop that revolutionized high jumping, the Zeer pot providing refrigeration without electricity, and the Phillips screw that enabled mass production. TRIZ teaches us that contradictions are not obstacles to avoid, but opportunities to innovate. The harder the contradiction, the more valuable the solution. Technical systems evolve predictably toward greater ideality. More benefits, fewer costs, less harm. Understanding this helps us anticipate and shape future innovations. Most importantly, TRIZ demonstrates that you can learn to innovate systematically. You don't need to be a genius. You need to understand principles and apply them thoughtfully. Innovation is not a mysterious gift. It's a skill that can be developed through practice and systematic thinking. TRIZ gives you the framework to develop that skill.